Hey everyone, welcome to this talk on the FH EVM, or how to build fully homomorphic encryption into the EVM. So everything on the blockchain is good, is public, which is good for transparency, but of course it also has some privacy issues involved with this. One of them being that criminals know who to target. You might feel like you're exposing too much information. And in other words, without some privacy, there are certain applications and certain use cases that we can't really unblock and find full adoption for. So our solution is to use fully homomorphic encryption to get around this problem. And without going into too many details about fully homomorphic encryption, come find me afterwards if you're more interested. The general idea is that with fully homomorphic encryption, you can encrypt data and you can compute on this data without decrypting it. Okay, so for instance, in this slide, we have two encryptions, an encryption of X and encryptions of Y. We can then do a homomorphic operation on these two ciphertexts and obtain a third ciphertext, which is now an encryption of X plus Y. Likewise, we can do a homomorphic encryption where we compare the two, and now we obtain another ciphertext, which is then the result of this comparison. And again, without decrypting anything. And more generally, we can take encryptions of values and we can apply a function to these ciphertexts, and then get a new ciphertext where this function has been applied essentially on the plaintext. Okay, so in the context of blockchains, this makes it possible to take input from the user, send it to the blockchain, encrypted, have the blockchain process this data while it remains encrypted, and we can keep it stored on the blockchain at all times. So, and we can do this without compromising transparency and usability. So in other words, we don't have to hide what computation is being done, so users can still inspect the smart contract, still see what kind of logic it's executing. They just can't see the data that it's computing on. We can also allow smart contracts to have their own access control logic, as we'll see in a bit, where if they want to implement some fancy way to kind of satisfy the need for the application, they can still do that. And we also get composability in the sense that you can mix smart contracts and have them share data like you typically do without encryption, but also you can easily mix data coming from different users. So if you want to build a blind auction where you take data from multiple users, then this is also not a problem with fully homomorphic encryption. So some of the use cases to go a bit further we can imagine with this is we can build trustless bridges in the sense that we can take the signature key, we can encrypt it, we can put it on chain, and then we can homomorphically generate the signature. So in other words, we can have a smart contract that will generate the signature. We can build the blind auctions where we don't have to leak any information besides the final winner of the auction. So no one gets to see the individual bids because they're all encrypted. You just get to see the final result. And you can do voting where you don't have to reveal how much you're staking or how much you're bidding for a particular vote. So some of you also know or think of zero knowledge when we say privacy. And it's true that zero knowledge does give some privacy. The way we see it is that zero knowledge is more technology built for scalability, think in terms of roll-ups. And one of the benefits of FHE is that it doesn't get in the way of composability. One is around contracts, but also especially around mixing data from multiple users. So in zero knowledge, you need someone to see all the plaintext data when you want to do the computation and then generate a proof that the computation was done correctly. With fully homomorphic encryption, you just have all the data encrypted and anyone can perform the computation. So you don't need some entity or single entity to see all the plaintext data. The computation is happening directly on the ciphertext. And also it's very easy to keep all the data on chain. So again, you don't need to have data stored off chain that can become unavailable and so on. Okay, so our solution to this, the FH EVM. Let's have a look at what it does. And the first thing to note is that everything is encrypted under the same public FHE key. So we generate a global FHE public key, and this is what makes composability so easy to do. Here we have the dots represent validators that now have this kind of global public key that users and so on can download. The way that we get this public key is that we start out having nothing, and then we run a threshold key generation protocol that will basically generate shares of this of the corresponding secret key to the global FHE key. And what this means is that no validator on their own can do anything with the private key that's used for decryption purposes because they only have a share of it. So they need to come together, a certain threshold of the validators need to come together and agree that, okay, now we want to use the secret key for something. But again, no validator can decrypt anything on their own. Then when the users want to provide input, they simply download the global public FHE key, they perform a normal encryption, and they send this to the ciphertext. And now the validators all know the encryption of the input. When they want to process on the input, so here we have an encryption of X, encryption of Y, they can use operation in our FH EVM to do the operation, to kind of apply the homomorphic operations to the ciphertext and then generate the ciphertext of the result, in this case EC. And sometimes we want to decrypt values. I'll get into it and we'll do a demo here in a bit. We'll see where we need to do decryption. But if the validators individually decide, okay, the smart contract dictates that now we have to decrypt a value here, then we can run a threshold protocol to do decryption, where each validators will enter the threshold protocol with their share of the decryption key, and then securely they will generate the decryption of this, obtaining the plain text. We can also do something else which we call re-encryption, where the validators, besides having shares of the global key, they also have, in this case, a blue public key, for instance, coming from a user, and they have a ciphertext X, and then without decrypting X, in this case, or the encryption of X, they can re-encrypt X under this new blue public key. Okay, and we'll see why this is useful on the next slide. But again, this is done in a secure way so that X is not actually revealed to the validators. It's rather re-encrypted under this other key. And of course, the use case for this is that when users, it's useful to have all the data encrypted on the chain and so on, but at some point you also want to decrypt this user, or this data and get it back to the user. For instance, if we're building a token and the user wants to see the balance needs to be decrypted at some point. The way we do that is we run re-encryption first, where we take the encrypted balance of the user, we re-encrypt it on the user's public key, and then the user can just call a view function to download this ciphertext and decrypt it because he knows the corresponding secret key for the key that he just supplied to the blockchain. Okay, we are not launching a blockchain. We're rather providing the components that allows anyone to build encryption into their blockchain. In particular, the components we have is this FH EVM that allows you to do homomorphic operations that can trigger these threshold protocols. We also provide the threshold protocols for doing this. They're highly optimized for the encryption scheme that we're using, TFHE. We're also providing a Solidity library that makes it easy to express smart contracts operating on encrypted data. This is done without having any changes to the Solidity compiler, so you can use your normal developer tools. You just import our library and then you compile a smart contract with this. And finally, we have an SDK for building dApps that allows you to encrypt data in the proper way and interact with an encrypted blockchain. Okay, but let's try and do an actual demo of this. And I tested and it did work, so let's see if it still works. Okay. All right, so far so good. Okay, so here we have normal remix. What I did is I cloned our example repository, so you can do this after. Bigger? Yep. Is that better? Yeah, cool. All right, yeah, please let me know if any of the screens are too small. I'm happy to make bigger. Okay, so I just cloned our example repository here, created a smart contract, and then let's try to build it and show some of the concepts that goes into it. So we'll start out just building a simple ESD20 contract here. We'll have an owner. Let's make it public. Oh. We'll have a constructor. Say that, okay, only whoever created the contract is now the owner of the token as well. And then we have our typical mapping where we map an address to a uint32 as the balances. Okay, nothing fancy so far. So the first thing I want to do is, for this particular token, I want to make the balances encrypted. So what I do is I import our library. Sorry, I got my cheat sheet here next to me. Which is also available on NPM. So this is just because I'm using the example repository we provide. And now when I import a Solidity library, one of the things I get is I now get an encrypted integer type. So what I'm now saying is that I want my balances to be encrypted. I'm not touching any of the other data, so you can freely mix public and private data, but I want my balances to be encrypted. And if everything goes well, I should be able to compile this. Yeah? Okay, and I could now deploy this on the blockchain if I wanted. But let's add a bit more functionality first. So the first thing I want to add is a minting function. So let's say we want to mint, or be able to mint. And I want to take an encrypted integer. So now whoever mints mints tokens are not providing the amount they want to mint in plain text. They're rather providing an encryption of the amount that they want to mint. And let me just see here. This is public. Okay, and then I'm going to require that only the owner can do this. And I'm simply saying that, okay, the owner is... And now I'll take whatever he has currently, and I'll add this amount to it. So one thing we're adding in our next version of Solidity library is the ability to use operator overloading instead of calling these things. So that stuff was going to be fixed. Okay, so now, yeah, we have our mint function. And this is valid and useful, but it's not exactly what we want. So in order to understand that, we need to understand what is this EUINT32 actually. And in reality, an EUINT32 is a handle to a ciphertext that's stored on-chain. So concretely, it's the hash of that ciphertext. And what we want here instead is we want this function to be, or this input to be provided from the user in the form of a ciphertext. So in order to do that, I'm instead going to say, okay, these are now some bytes coming from this, and I'm saying this is the ciphertext I get as input. And then what is the correspondence between this amount and the amount ciphertext? Well, I can get an EUINT32 amount by converting it as EUINT32 and then amount ciphertext. Okay. And the reason we have to do this conversion, so to go from the kind of the raw ciphertext into an EUINT, there is one critical reason for this, and this is when we do the conversion here, when we convert from the bytes into an online value, we're actually performing two checks, which are critical for security. The first one is we're requiring that the ciphertext is well-formed, what is called, and this is a cryptographic requirement that for this particular ciphertext or encryption scheme, if these were just random bytes, then a user could try to potentially learn something about the secret key. So the encryption scheme inherently requires that there is a proof that this ciphertext is well-formed. The other thing we're doing here is that we're checking that the user that provided this knew the underlying plaintext. And the reason for this is that imagine a user that goes on the blockchain, grabs a ciphertext, and then inputs it to a smart contract and asks that smart contract to decrypt the value. This will break the entire security of the chain because we can't just use the blockchain as a decryption oracle in this way. So intuitively, if we can ask the user to prove that he already knew the plaintext that was inside the ciphertext, then he wouldn't learn anything else or anything new if he was doing this. So what's included in the ciphertext is a zero-knowledge proof that one, the ciphertext is actually well-formed from a cryptographic perspective, or required from a cryptographic perspective, and then also that the user knew the underlying plaintext. So we get around this misusing the blockchain as a decryption oracle. Okay, and then now that we have an EUINT32, we can start using it in our system. So an EUINT32 really represents a ciphertext that's stored on-chain and is ready for processing, that the system can process, whereas the ciphertext that came in here are just the raw bytes that are so far kind of untrusted. Okay, so let's see this working. Is this clear, by the way, the distinction between these two? Okay. So I compile it here. I cheated a bit. I already copied the ABI, so we have that. But now let's try to deploy it. So I'm using MetaMask here. Let me check I'm on the right account. Yeah, I'm a developer. I'm going to deploy this. So I said we're not launching a blockchain, but we do have a DevNet for those that want to experiment with this. I'll get to that in a second. I confirm. Okay, connection is good so far. I copy the address. And then over here, I have a few sample codes where we're using our JavaScript SDK, it's the SDK for interacting with an encrypted blockchain. So I'm going to say contract, it's the one we just deployed, npm run, and then mint. What we do here, if we look in this mint function, is we instantiate the SDK, we encrypt a value, in this case a default of 1,000 because I'm not specifying it, as an EUINT32, or a 32-bit integer. And then we simply send this transaction to the blockchain. All right, fingers crossed. While that completes, we should be able to look in our block explorer here. It should be, for this one, maybe it's a bit small. Okay. So let me just check that it went through. Yeah, looks good. So what we see here in the payload is a bit hard to decipher, but this is the ciphertext that's being sent. So I know this is not really meaningful, but this is to show that we're not actually sending the plaintext. Right? You can go here and you can grab the ciphertext if you want to. This ciphertext is about 8 kilobytes. We're working on getting that smaller, but it's not terrible. Okay, and we also now have the mint. So the next thing we might want to do is try and actually see that this worked. So to try and get our balance. Sorry? So that's one thing that we tweak with the EVM, that we say the gas calls for these operations are tweaked to this. So with what happens under the hood, good question, is we're not compiling everything down to EVM bytecode because the homomorphic operations would be too expensive to doing that. So what we do in the FH EVM, or one of the things we do there, is we add precompiled smart contracts for the homomorphic operations. And then in those precompiled smart contracts, we're calling out to our encryption library to do the actual operations, so the heavy lifting. So we can tweak the gas calls for individual homomorphic operations instead of having everything as EVM bytecode. Okay, so let's try and add this balance. Now that we know what this EUN32 is, we can also see why this is probably not what we want. Intentionally, I didn't make it public here. And the reason is this is, okay, the user, if they want to go and get their own balance, if we expose it just like this as a public, they wouldn't just get a ciphertext that's encrypted under the public global key that they can't decrypt. They will get a hash of a ciphertext that they can't decrypt. So what we want to do here is we want to inject some logic. So I'm going to make this one internal. And then I will define a balance of function here. And as I said before, we could ask the blockchain to just decrypt this value, and then they could read it as a plaintext value, but that would also leak this thing to the validators. So what we really want to do here is we want to do this re-encryption. And to do this, we're going to take a public key from the user, and then return, say, bytes memory, where we can use a function provided in Solidity library called re-encrypt, where we're taking the balance of the caller and asking it to be re-encrypted under the public key provided. And if this balance happened to be uninitialized, we want an encryption of 0 instead. Then I have a typo up here. Okay, so this will work. So what this will do is it will ask the user when they call this function to provide a public key, and then they will run the threshold protocols among the validators to then re-encrypt the balance under the global key and to the user supply key and send it back to him. Now, there is one security issue here, and the thing is, since this is a view function, nothing is signed. So we're getting a public key and we're getting someone that pretends to be a specific sender. And this, of course, he could impersonate anyone he wanted to do. So one way around this is to add a signature to it. We're not dictating how people want to do this, so this is free for you to do. But one nice way of doing it is to use EIP 712, which when the user is then signing his public key, we can actually give him some intelligent message about what he's signing, instead of just saying, okay, you're signing this random message that doesn't make any sense. So it's a way of putting structure onto this custom message that we're asking him to sign. And for this, I'm going to cheat a bit. So we have here an EIP modifier that I'm just going to grab. First, we need to import this. Okay, and then I have a pre-cooked modifier. What this does is, it works with this EIP 712, is basically the public key, or we expect a signature on, in this case, then it certifies signer message. We are now taking bytes. Let me just get this right. Signature as well. And then we will require that only signed by sender. Public key. Oh. Make this work is I need to say that this one is EIP 712. This is just some boilerplate to make this work. Oh, sorry, wrong. And then I need to pass this to the constructor. Okay, so the key thing here, thank you. Okay, so the key thing here is we now added a signature to the public key. And we kind of decided on our own how we wanted to do this. All right, so let's try to deploy this. copy it. And let's see if we can call it. Sorry? Typo? Oh, yeah. Thank you. Oh, there's two actually. All right. Okay. So to look at the JavaScript or the SDK side of this, so what we do is in our SDK we also provide a way of generating these tokens, or authentication tokens as we call them, conveniently for you. So this is, we're generating, under the hood we're using Salt and ACL to generate these public keys, and then we're generating the signature as well. So here inside the token, we're getting our public key, and then we can send in a signature. So we're just providing a convenient way of doing this on the SDK side as well, or the dApp side as well. Then when we call the balancer function, we get the encrypted balance back, and now we can, since we generated the public key here, we can then also ask our SDK to decrypt this value for us. Again, just using Salt under the hood. All right, let's see if this works. Okay, so far so good. We have a balance of 0. So let's see if we can, what happens if we mint a bit.
Did it show up in the Block Explorer as a deployed contract or something?
Yes, let's have a look. So here we created a new contract, and then here's our mint function, or mint transaction. Okay, so mint should be done. So let's, hopefully our balance is now 1,000 because we just minted 1,000 tokens. Okay, so the last thing I want to show is how we can do a transfer as well. That's also useful in a token. So function transfer. And then we say, okay, who are we transferring to? And then again, this is a function we expect the user to call. So we're not accepting an EUINT32, we're accepting a ciphertext that can be converted into an EUINT. So we say here, bytes, call data, amount, ciphertext. That's a public function. We now convert this amount, TFHE, as EUINT 32. Amount ciphertext. Okay. Do I have that? No? Oh, good. Okay. And then we can also use one thing you want to do when you want to make a transfer is you want to make sure that this amount is actually on the user's account. Right? So we say, okay, we now have another encrypted type, which is a Boolean in this case. We say, okay, do we have sufficient funding on this? So TFHE less than, and then balance of message.sender. Okay, and then we require that there are sufficient funding. Now, this won't work, right? Because we have an encrypted value here, and in order to run and require a plaintext operation, we need to decrypt this. So what we do here instead is we have a require, and what this will do is it will instruct the validators to decrypt this Boolean value. We're not decrypting the inputs, so we're not decrypting amount or the balance. We're just decrypting a Boolean value that will tell the validators whether or not to continue with this transaction or not. And if this Boolean value turns out to be false, then we abort the transaction. And if it goes through, then balances 2 is now whatever it was before, plus this amount. And we need to subtract it on the sender as well. Okay. Let's try to compile this. Gonna deploy it. So contracts, npm run. Well, we need to mint something first now because it's a new contract. So let's do a quick mint. All good. Let's check that we have some tokens. Oh, balance of. Okay, all good. And then let's try to make a transfer. Looking at the transfer script here, Nothing exciting. We're encrypting the amount that we want to transfer and then just calling the transfer transaction. So we say npm run transfer. Now we want to specify who we're transferring to. And I set up a different account here. Let's go and grab the address. Oh. So in this case, we're encrypting a default value of, or transferring a default value of 100. Okay, and now if we check our balance off, should hopefully be 900, which it is. Okay, so let's also see this. We have a quick demo website here where I can put in my contract. There are a few, by the way, you can go and play with. ERC20, blind auction, private betting. For now, we're just sticking to the ERC20. I put in my contract address, and as the recipient. So this is what I was talking about before with the EIP 712, that we're now getting the balance right. So we need the user to sign his public key. So he needs there's an interaction with the wallet, and in order to make this message a bit more useful for him or a bit more meaningful, we can use EIP 712 to actually say, okay, we're doing a re-encryption here. You're sending a public key and so on. So we ask him to sign that. We get a response back from the blockchain that he has 100 tokens. And just for good measures, we can also try and switch to kind of our developer account that we were using that owns the contract. Get the balance. We now need to sign again because we're on a new account, and we have 900 here. Okay, that concludes the actual demo. Any questions on the code part of this?
Yeah, so I'm a bit puzzled using this homomorphic encryption for the tokens balances. So what prevents a node operator from running this DFHE dot lesser than operation locally and then doing simply just binary search and extracting the balance of the user?
So binary search as a smart contract?
Yeah, I mean, he's running it locally, right? It's everyone can run it locally, and he can just add another function to the smart contract saying find balance, and he uses the existing public key of the user and the homomorphic key and so on, and he just called it in a loop, doing binary search across possible balances and then shrinking where the balance stops, and then it checks the balance this way.
Right. So and you can do that as an individual validator, but you need to convince all the other validators to run exactly the same code. Because when you then do the actual, otherwise you're just getting a bunch of encrypted booleans, and you have no idea if they're true or false. So when you want to branch in your binary search, you need to decrypt that value. So if you want to do this, you need to convince the other validators to do this. And that's why, as a user, it's still important that you look at the smart contract code to make sure that they're not trying to guess your value by doing a binary search or something like this. Because a single validator will get a ciphertext, but he can't decrypt that ciphertext. He needs all the other a fraction of the other validators to run the decryption.
And how is this done in practice? I mean, do they communicate with each other to obtain this?
Yeah, okay, so we can go back in here.
Transfers basically handling this re-encryption.
So in this case, it will be a decryption, but each validator only has a part of the decryption key. So he needs to convince the other validators to then do the decryption with him because they have the other parts of the key. So it's true, you have to be careful that the contract itself is not leaking too much with these requires. So as a user, it's still your responsibility to go and say, when I send my data to a smart contract, is that smart contract trying to do a binary search that leaks too much? But a validator on his own can't do this. He can deviate from the smart contract, of course, if he wants to, but he still needs the other validators to actually do the decryption of the value to learn anything. And that means he needs to convince the other validators to run the same smart contract code.
Was there, like, in the transfer JS, like, some re-encryption going on? Or maybe it was
In the balance of?
Balance of, yeah.
Yeah.
So is that like simulating the validators talking to each other to do the re-encrypt? Because I guess in the re-encrypt you also need the threshold, right? Like on the line 22, you're saying like, Oh, that's okay.
So-
I was okay. That was just the 712 message. Okay.
So what's happening here, if we look at the slides, is there's two steps happening. The first thing is that in our Solidity code, we had the re-encrypt call. Right, so this was balance off. Here, we're asking the blockchain or the validators to re-encrypt under a new public key that came in from the user.
Right. So that's kind of like triggering the validators to do the.
Exactly, that's this step. So now we assume that they have the public key from the user, the blue key here, and now with the smart contract is asking them to re-encrypt this ciphertext that was under the global FH key to the ciphertext that's on the user-supplied key by the re-encrypt call. And then afterwards, when we have the ciphertext on the user's key, he can just download this using a normal view function, right? This is just data that's now available to him. And then since he knows the corresponding private key to the blue key, he can then decrypt on his side. So that's what we saw in the, here, that he's up here he's generating the blue key, and then we're asking him to generate a signature on this using his wallet. And then when he get the encrypted balance back from the blockchain, so this is now the blue ciphertext, he can of course decrypt this because he knows the corresponding decryption key for the blue key.
I guess that's why you need your own like EVM, because you're doing it in the middle of the transaction, right? So in the middle of the transaction, the validators must coordinate and then continue executing it. So otherwise it would be more like some chain link callback sort of thing.
Yeah. So exactly. So there's two places where this happens. One is, if you look at the Solidity code, when you do the re-encrypt, we're triggering the threshold protocol to re-encrypt under the new key. And when we're doing the require down here, we're triggering a threshold protocol to do a decryption of just the Boolean value to know if they continue or not.
Yeah, I have two questions. So, do you have any number of performers of this threshold key generation or decryption protocol? So, and how many participants are involved? I think this is crucial to the whole system, right?
Yeah.
And my second question is that if I'm correct, the validators will recompute every homomorphic operations, right? So do you guys think of using like outsourcing these computations using stars such as that?
Yeah, good question. So what we're targeting for is, again, we're not providing our own blockchain, so we want to be a bit flexible here so that people can build whatever corresponds to their use case. We're targeting two scenarios, one where we have a handful of validators that want to do this, and one where we have around 40 validators at a time. This can change over time, so we also have resharing protocols where you go from one group of validators to another group of validators, and then you reshare the shares of the private key as you go along. But those are the use cases we're targeting.
Kind of heavy MPC protocol because you have to apply general proofs to prove the validity of all the public keys or the decryptions. I think it's a little bit heavy, but that depends on the number of validators, right?
Yeah. So the protocols that we do, because as I didn't say this in the beginning, Sama as a company, we're specializing in homomorphic encryption, and then we're building this on top of it. So what we do is we specialize on one particular encryption scheme, TFHE, and then what we can do with the threshold protocols is we can heavily optimize them for this particular encryption scheme. So that's why decryption is actually very efficient, even when you're running this between like 40 validators. The other question you had around performance for the initial key generation, that could be a more expensive operation, and it is, but it's only happening once during genesis of the blockchain.
So do you try to using stars to outsourcing all the homomorphic operations?
So good question. So the thing is, when we do the operations, all the validators need to perform the homomorphic operations, and these are more expensive, of course, than normal plain text operations. So the question is, can we outsource this heavy computation to powerful instances? Yes, we could, and we're looking into that. We have research going on that. The problem is that if you wanted to build these zero-knowledge proof of correct computation over the particular mathematical object that the zero-knowledge scheme is working in, it doesn't fit exactly. So we're working on adapting that to that and then being able to do verifiable computation on FHE.
Thank you, guys. Sorry, we are running out of time. We have to move for the next conference. But if you have any question, feel free to ask the speaker after.
Let me just add one quick thing. So we're actually doing a hackathon Friday, Saturday here in our Paris office. We're a Paris-based company. So if you're interested, go have a look either on our website, scan the QR code, and we'll be happy to see you there.
Thank you very much.
Thank you, everyone.